Hello, my name is Jordan Barkai, and I'm making this video to present to you the work from my recently published paper, a comparative study of source-finding techniques in H1 emission line cubes, using SoFiA, MTObjects, and supervised deep learning. This research was done in collaboration with Verheijen, Martínez, and Michael Wilkinson. As the technology used to create astronomical surveys improves, an unprecedented amount of data will become available. Hence the need for fast and accurate techniques to find sources and reduce the time and difficulty of doing so manually. The current challenge lies in the absence of the boundaries of sources, with many having intensities very close to the noise. This has led to a trade-off between completeness and purity. Atomic neutral hydrogen, also known as H1, is one of the primary wavelengths observed in radio astronomy and can be used to determine the structure of galaxies. However, it is intrinsically faint and sensitive to its environment, requiring large volume coverage to map the H1 universe. Here you can see a fly-through example of an H1 emission cube, containing sources and noise. This video nicely shows the problem at hand, trying to find and mask these galaxies amongst non-uniform noise. In this work, we aim to find the optimal source-finding pipeline for such large volumes of H1 emission data. In recent years, a variety of astronomical source-finding software has been developed, inspired by traditional computer vision methods. We compared two of these traditional methods, the well-known H1 source-finding tool SoFiA, which makes use of the smooth and clip method, and MTO, which makes use of max trees and has been found to outperform other methods in optical source-finding. These two methods were also compared to a volumetric convolutional neural network, known as V-Net, in order to find the best source-finding pipeline for H1 emission cubes. This was done using H1 emission data cubes from the medium deep imaging survey of the aperture tile in focus, or M.H.F. While these observations provide a large amount of data, the sources within them are unlabeled. Therefore, simulated galaxies created by a Van T Go gate with labeled masks were inserted. A binary mask was then created for each data cube and used as the ground truth to evaluate all three methods. Once all three source-finding methods were run on the data, a random forest was used to filter out false positives from the resulting catalogs. Real sources contained in the original H1 emission cubes were identified by cross-matching them with the optical catalog pan stars. All of these experiments were evaluated separately for marked galaxies and real sources, using a score combining the purity, completeness, and the overlapping of the masks with the ground truth. While SoFiA performed best overall, V-Net was a competitive second, struggling only to properly mask intrinsically asymmetric sources, since the network was primarily trained on symmetric mock galaxies. This suggests the potential for the V-Net network to outperform SoFiA overall, with an even better mask quality should it be trained on more real sources. While there are some limitations to these results, and room for future work, the everyday applications of computer vision and the amount of astronomical data continue to increase. This paper demonstrates the need for astronomers to keep up to date with the advances in computer vision as this progresses, and as these methods become competitive with traditional approaches. If you were intrigued by this brief video and want to find out more, the article itself can be found in Astronomy and Astrophysics and the preprint in Archive, both of which links have been added in the caption.